We're now going to see an example of how to find the relative extrema on a surface. The first thing that we need to do is to find the critical points. And in order to do that, we'll calculate the first partials with respect to x and y and find the AB ordered pair in the domain that causes both of these first partials to have an output of 0. We'll also look for domain elements that cause either of those first partial derivatives to be undefined or to not exist there. Once we have those critical points, we'll use this second derivatives test to determine whether or not we have a maximum, a minimum, or a saddle point. So let's begin our example. Again, the first thing that we'll do is find the critical points. In order to do that, we're going to calculate the first partial of f with respect to x, and then the first partial of f with respect to y. With respect to x, we hold the y values constant, so the derivative of negative x to the third power is negative 3x squared. If 4 and y are constants here, this derivative is just going to be 4y. And if these terms are constants, their derivatives are 0 with respect to x. And now the first partial with respect to y, this term goes to 0. 4 and x are now the constants on this term, so the derivative is just going to be that constant multiple. With respect to y, the derivative here will be negative 4y to the first power, and the derivative of this is just 0 as well. So to find our critical points, we're going to set both of these equal to 0, and then find the xy ordered pairs that solve this system of equations. And there's a couple ways that we can do this, but I'm going to solve this system by elimination because I see that I have 4y and negative 4y that cancel each other out. When I add up all the terms on the left-hand side, I'm going to get negative 3x squared plus 4x, and then add up on the terms on the right, I get 0. And then I can factor this out pretty easily. I'm going to factor out an x to get negative 3x plus 4, and then set each factor equal to 0. X is equal to 0, negative 3x plus 4 is equal to 0. So my solutions to the system are starting to unfold. One x value is x is 0, the other, I'm going to subtract 4 and divide by negative 3 to get x is equal to positive 4/3. Now the solutions to this system of equations are going to be ordered pairs, one of which has an x-coordinate of 0 and the other has an x-coordinate of 4/3. Let's come up to our system of equations and grab this one, pull it down, and use it to find the y values, the corresponding y values. If I divide everything by 4, I can more easily see that x and y are going to be equal to each other. So my y-coordinate is 0 here, and my y-coordinate is 0 here. So far, I have two critical points. So we found the AB ordered pair that makes both first partials equal to 0. Now let's look and see if there are any ordered pairs that make either of the first partials not exist. Well, since we don't have any x or y values in the denominator of a fraction, underneath a radical, we don't have any x or y values that are not allowed to be plugged into these first partial derivatives. So no matter what real numbers I plug in for x and y, I'm always going to get a real output, so these first partials are going to exist everywhere. There are no domain restrictions for these first partial functions, which means that these are our only critical points. So after we find our critical points, the second thing that we need to do is to plug those into this second derivatives test. And in order to do that, we'll need to calculate these second partial derivatives with respect to x twice, with respect to y twice, first with respect to x, and then with respect to y. So let's begin by calculating the first partial with respect to x twice, which means we start with the first partial with respect to x and differentiate it with respect to x again, which means that we'll be holding these y values constant, and if y is constant, this derivative is going to go to 0. With respect to x, this term has a derivative that's negative 6x to the first power. So just to clean that up, we'll say fxx is negative 6x. So now we'll look at the second partial derivative with respect to y twice, which means we're going to begin with the first partial with respect to y function and differentiate that with respect to y again. So we're calculating the partial derivative of this function now holding x constant, so its derivative is going to go to 0, and the derivative of negative 4y is just going to be negative 4. So again, let's clean this up. Fyy is equal to negative 4. Now we need to determine the first partial with respect to x, differentiated again, but this time with respect to y. So that's first partial with respect to x function, differentiated with respect to y the second time. So we begin with the first partial with respect to x and differentiate it with respect to y, which means that the x values are constant and this derivative is 0, and the derivative of this term with respect to y is just 4. So let's clean that up again. We have fxy is now just equal to 4. So now what we'll do is we'll take our critical points that we found, remember 0, 0, and 4/3, 4/3, and we'll take these critical points and calculate the d value for each of them. So just as a reminder, here is our formula for that second derivative. So now we're going to calculate the d output evaluated at each of our critical points, which means we calculate the second partial derivative with respect to x twice and see what that is at our critical point. Second partial derivative with respect to y twice and see what that is evaluated at our critical point, and second partial derivative with respect to x and then with respect to y evaluated at our critical point as well. So plugging 0, 0 into our second derivative test, we get 0, 0 into fxx is going to just be equal to 0. And then we multiply that by 0, 0 plugged into fyy. And since fyy is a constant, that's going to be multiplied by -4 minus 0, 0 plugged into fxy, which is also a constant, is going to give me 4 quantity squared. This product is just 0 minus 16, which is less than 0. And when we come back up to our second derivative test, we see that if that d value is less than 0, then we end up with a saddle point at the ordered triple on the surface. So therefore, the ordered triple, 0, 0 as the domain element, and then whatever the function is evaluated at 0, 0 to get the z-coordinate is going to be a saddle point. So let's see what that z-coordinate is. So let's come back up here to our surface and evaluate the function at 0, 0, we're going to get 0 plus 0 minus 0 plus 1. So this is all going to give me just 1. So since the z-coordinate is 1, let's fix up this ordered triple to be that we have a saddle point at the ordered triple 0, 0, 1. So that's what's happening at one of our critical points. So now let's test the second critical point, which was 4/3, 4/3. And again, we're going to plug this into that d formula. So that means we'll look at the second partial derivative with respect to x twice evaluated at 4/3, 4/3 times the second partial derivative with respect to y twice evaluated at 4/3, 4/3 minus the second partial derivative first with respect to x and second with respect to y evaluated at 4/3, 4/3, and that quantity would then be squared. So if we evaluate the second partial derivative with respect to x twice, we're going to put x is equal to 4/3 into here and get -6 times 4/3. So this will be -6 times 4/3 times, now we need to look at the second partial with respect to y twice, evaluated at 4/3, 4/3, which again is equal to the constant -4. So we multiply this by -4 minus quantity, second partial derivative with respect to x first and then with respect to y, evaluated at 4/3, 4/3. And that was also a constant 4, so we're subtracting 4 and squaring that quantity. So this second derivative quantity turns out to be, let's cancel the 3's here, so we get -8 times -4 minus 16, which is positive 32 minus 16, which is 16. And since this is a positive value, we need to consider one more thing. In the second derivative test, it says if that d value is positive, then we need to also look at the second partial with respect to x twice. And the sign on that quantity is going to tell us whether we have a maximum or a minimum. So if the second partial is positive, we have a max. If the second partial is negative, we have a min. So back down here, that tells us that we now need to look at the second partial with respect to x, evaluated at 4/3, 4/3, which we've already determined to be this quantity here that turned out to be -8. So since this second partial is negative, that means that we're going to get a minimum at the ordered triple 4/3, 4/3, and then the function evaluated at 4/3, 4/3 as the z-coordinate. So if we go back up here and we evaluate this surface function at 4/3, 4/3, what we'll end up with is the value 59/27. So we'll replace this with the actual z value and say that this ordered triple is a relative minimum. And let's bring our other finding down here so that everything is the same spot, and this is our final answer.